This video will talk about deriving the natural frequency, okay, and then what we need to do is that let's take a look into the staffs. We have a diagram. This is the diagram itself. We have when you have a mass, okay, mg, and then when you put it there, okay, when there is no external force, there will be a mg downwards, right? And then reaction force tells us that there will be a k delta t, okay, and then this delta t is some length between here, okay, where you pick a datum point, and then the datum point from the object itself, the mass itself, with a certain distance. So this is the distance, and then multiply by the k. Okay, so this is it. And then once you put it down, okay, once you have an external force, this is when you have no external force. This is when you have external force. You put it down, and when you stretch, you have another x value. So apparently, when it is static, it is just the spring constant multiplied by this length, um, and then is equivalent to mg, which is the mass. And then when you put it down, you have a certain distance x. So your force that you apply into this system is somewhat changing the distance x. So when you let it go, it starts to oscillate. So the very first equation that we need to introduce you is let me see. It's actually this equation. So we will have to derive. We will have to hold on. So apparently we have to eventually derive this one, okay, and then we put in certain stuff, and then we derive our omega n equals to k over m. So our final result is actually two equations, okay. This is the differential equation, the standard one, and then these are the one that we knew earlier in the previous module. And then so without further ado, let's start off with the derivation, okay. And I just want to let you know, this analysis is actually a free undamped vibration of 1 degree of freedom system. Free undamped means that there is no damping system, okay. Even there is no air. Normally air resistance, there will be air resistance for damping, but now we're talking about when there is no resistance at all. So it will keep oscillating and oscillating. And then 1 degree of freedom is that you are going from top to bottom to top. So it's just one axis, so 1 degree of freedom. And then a simple undamped spring mass system. So we have a certain consideration that a simple undamped mass system with only vertical axis because 1 degree of freedom, as I mentioned. And then it's in terms of x, okay. And then oscillation will take place and at natural frequency. So when you start to put it down and then you just start to go, you go in the natural frequency form, okay, unless there's external forces. So and then the fifth one is what we have drawn, the picture over here. If you know why am I putting all these numbers, just to say that these are all the labels step by step, so at least we are not lost in the steps. So 5 and 6. So this course needs to, so apparently now we are trying to, typically I would stress that we have to draw free Doric diagram. Okay, I don't know whether I put it in the summary. The typical, okay, never mind, it's not in here. You have to first, okay, maybe I should go, I paused the video. Okay, this is actually the lesson 2 one, but I just want to put it here. So apparently for analyzing certain stuffs in terms of dynamics, you have to first understand the movement. So as we know, we already understand the movement over here, and then we start to draw free body diagram. So then free body diagram means that we have certain force over here and certain, reaction force, and then when you have certain external things, and then yeah. So these are the free body diagrams, and then once you have that, and then you summation of moment. So you have to come out an equation that is summation of moment, meaning the law of conservation. So conservation meaning what comes in must come out, that kind of thing. So yeah. So and then find ways to simplify the equation and get answers, whatever your answers you want. So apparently this is the this one step is one of the biggest problem, because once you set up the equation, you have to linearize them and make them easier to derive your whatever you want. Okay, and then yeah. So what we where am I? Okay, so so therefore we are more concerned of the free body diagram, and then we have already drawn the free body diagram. We have really understand the system. So let's come up with an equation. Okay, so we know that mg is equals to k delta st, the static, I would say, I think so, static equilibrium. And then as you know, as I say, when you leave it static, there is no external force. Mg is equals to the reaction force of this one, right? In order to hold it there in a static equilibrium state. So therefore we can deduce that mg is equals to this, and then we know that Newton's second law, F equals to ma. So we just sub it in, okay? So we have plus mg, okay, is a downward force, because as you know it's going down. So we deduce by then, okay, I also need to tell you something. When you set up your free body diagram, you also have to clearly state your V sign, meaning minus and plus, whether towards left it's plus, or towards right is plus, or whatever, or maybe anti-clockwise is plus, on clockwise is minus, or whatever. So when you're doing this, is very important. And then yeah, so let's come back here. So we know that we are going down, yeah. So we set downward motion as a plus, positive, and then force upward is negative, okay, and then equals to mass times acceleration. So it's the movement of the thing. So we have this equation, and then mg is equals to this, which is the same thing as this. We set it as equation 1, and then hold on, give me a moment. Okay, so this is trying to set up an equation for this thing. So apparently, since we know that mg is equals to k delta st, so we just sub it in into this equation, okay? And then since mg is equals to this, we just sub this thing into here, okay? So when we sub this thing into here, you get this one, okay? And then minus when you multiply k into here, you get this thing. Actually, this is delta. Okay, I didn't write it properly. It's actually not f. Okay, this is delta, same as this. So equals to I believe is mx dot double dot. Okay, it should be ms double dot. And then what I mean is that okay, this should be mx double dot. So apparently, when you cancel out this thing, this one will cancel to 0, and then minus kx, left minus kx is just bring it over, you have plus kx, sorry, it's equals to, where am I, is equals to 0, and therefore mx double dot plus kx equals to 0, we have this. So we have derived the first equation, the often used equation. You have to put it in your mind, equation. And then this equation, also you have to put it in your mind, is that this equation reflects the the motion of mg is equals to k delta st. Okay, so it's just a relationship between mg equals to k delta st, that's all. Okay, so it's just a relationship between this mg and its reaction force with a second moment of area, and then you can set up the equation this. So I'll just end here, and then next video I'll just talk about how to derive this one. K equals to, the natural frequency. So next video I'll talk about this. So yeah.